So our next presenter is Jack, and Jack is a PhD student who received his bachelor degree from the Engineering Science program at U of T in 2017, and his current research focuses on evaluating the impact of climate change on structural loads and investigating how to propagate wind turbulence information from large-scale climate models to small-scale computational fluid dynamic models. So welcome, Jack, and you're up.
So my background comes from structural engineering. So my research is basically on how the climate affects infrastructures from a structural engineering point of view. And these are my team members. We also have collaboration with NCK and Environmental and Climate Change Canada. So like the wind load is related to the climate. So my research is on how the change in weather pattern are expected to lead to larger peak wind speed in the future and increase in the occurrence of frequency of extreme wind scenarios. As we know, a high-rise building can be vulnerable to long-term effects of climate change. It's quite important to assess how climate change affects this infrastructure. So the objectives of my research is to estimate future wind speed in downtown Toronto, and then compare and evaluate the future wind speed with what's calculated from building code, and then see what is the adaptability of the built environment. And for built environment assessment, we first start with the climatology. We estimate the future design wind speed based on some global climate model. And then we feed the data from those climate model to a smaller scale CFD model. And from that, we can extract the structural load and evaluate some criteria based on structural analysis. And finally, we can check if they are in acceptable level. So in this presentation, I will just highlight some of the main part we have gone through. So for the first part, we extract wind data from 19 global climate models. As you can see from the top left figure, the y-axis is wind speed and x-axis is the year. And then because these models are very large scale, we need to adjust it based on the local statistic. This large scale model do not capture small scale characteristic well. So we need to do a statistical downscaling to adjust it based on the observation we have. And we will allow this model to continue into the future to predict the change in viability and the change in mean wind speed in the future. And that's how our group obtained the future design wind speed for assessment of a building. So we plot, but there's some issue with, processing this large amounts of global climate model, because each of them are formulated differently, and basically you will get a wide range of results. So here, because here I'm plotting the histogram of different design wind speed of different models. So initially they quite converge because we adjust them to be almost the same. But as the year passed, as we go into the future, the model starts to diverge. And the divergence is even larger if we go into the next 30 years. Yeah. So this poses one of the difficulty for assessment of the impact of climate change, because basically we don't know which model is correct. If this model is correct, then we may need to reinforce some of our current structure. But if this model, if the model with lower wind speed is correct, maybe we don't need to do anything. There's not much risk. So yeah, from these analysis, usually we do a scenario-based analysis. We assume that certain model to be correct, and then we can feed the data into a CFD model to obtain yeah, the aerodynamics effect on tall buildings. And this is what the CFD model looks like. It's a small scale that simulates a wind tunnel test. And we usually have a building of interest, and we pass the simulated wind flow through the domain to obtain the pressure distributions. Yes. And then here is some validation we did for our model. Usually we are interested in the surface pressure coefficient of the building that's directly related to the wind load on building. And yes, as you can see here as well, the different, each curve represents a different modeling method of the CFD. The results are quite diverging as well as some location. And then this, the points on the right figure represent the wind tunnel test result. Even for wind tunnel experimental test results, like this pressure can differ by quite a lot. So this is another research area to quantify these uncertainties. Yes, so to summarize, yeah, currently there's some obstacle to study the impact of climate change is the uncertainties, the divergency of global climate models, and also different numerical simulation method leads to huge like errors or uncertainties associated with the future climate. Yeah, so yeah, there's currently a big research area to look into yeah, the quantification of these uncertainties. And also maybe we can aggregate or disaggregate some of this data to, so we can do scenario-based analysis. Yeah, so that's it. Thank you.